Hey guys, today we're going to be reviewing the rational functions and the properties of their graphs. And we're going to go over how to find all of these properties algebraically in order to prepare us on how to graph these functions later. Now we learned in the past that a rational function looks like this. It looks like a fraction where you have some polynomial probably or whatever function in the numerator and the separate function in the denominator. Now, if you're trying to find the domain of each rational function, the domain is restricted by what the denominator is equal to, meaning that we cannot have in any fraction where the denominator is equal to 0. So what we do to find the domain of a rational function is we do just that. We make the denominator, in this case for x plus 1 over x minus 4, not equal to 0, since the denominator is exactly that, cannot equal to 0. And then we solve for x. So in this case, I would have to add the 4 to both sides. So we get that x cannot equal to 4. This means that my function would be undefined, or there would be something present on the graph that would make the function like there would be either a hole or a vertical line that the graph cannot touch ever. So that means that our domain for this particular graph is all x's except for negative 4. So that would be from negative infinity to 4, union 4 to infinity. Now something that you may find helpful in order to write out your domain is put this on a number line. If my graph cannot equal to 4, that means that I have to exclude that number, but everything else would be okay. So that's why we would go from negative infinity, stop at 4 with a parentheses, because that 4 is not included, but then start again at 4 and then go to infinity. Let's look at this other example. We have 3x over x squared minus 4x plus 3. So what I want to do here is, again, make that denominator not equal to 0. Now in this case we have a quadratic. So in order to figure out what those x values are, we would have to factor. And this particular quadratic can be factored to x minus 3 and x minus 1 cannot equal to 0. And that's because negative 3 times negative 1 gives you the positive 3, and negative 3 plus negative 1 is the negative 4. And we learned in the past when we're solving that you set each individual factor equal to 0. Or in this case, not equal to 0. Because remember that we need to exclude these values from our domain. To solve for each x, in this case, I'd have to add the 3, so x cannot equal to 3. And in this case here, we would have to add the 1, so x cannot equal to 1. Now you can put this on a number line to help you visualize that domain, and we will write the two numbers that we got, 1 and 3, obviously putting your numbers in numerical order. These numbers are excluded, but everything else would be okay. So the domain would be from negative infinity to 1, again parentheses because it's not included, union, parentheses 1 to 3 because that middle section is also okay, and I put a parentheses around the 3 again because it's not included, union 3 to infinity. And that would be my domain for this particular function. Now for h of x is equal to x minus 2 over x squared plus 9. First you do the same thing as you did before. X squared plus 9 cannot equal to 0. Now if I were to try to factor this, I can't because this is not a difference. Remember that this could be a difference of squares if this was x squared minus 9, but it's plus 9. So instead I'm going to try to solve for x. That means that I would subtract the 9 to both sides. So x squared cannot equal to negative 9, and then square root both sides. And we get that x cannot equal, now here we have the square root of a negative number. So that means that we would have I, and the square root of 9 is 3, so 3i. If you ever end up where the denominator is equal to some imaginary number, that means that the denominator will never equal to 0, meaning that for the domain, it would be from negative infinity to positive infinity. Since the denominator never equals to 0, there is no problem. Now, let's look at a couple properties of rational functions. The first one is vertical asymptotes. Now, a vertical asymptote is an invisible line on the graph that the function will never touch. So in this particular case, for f of x is equal to 1 over x, this is, first of all, our most basic rational function, just 1 over x. And you can see here that we have a vertical asymptote at x is equal to 0. Now, to kind of prove that we have a vertical asymptote, you'll see these limits here. This limit says the limit as x is approaching 0. So we're looking at the graph from 0, and then here you see this little negative sign. This means from the left. And from the left, we see that the graph as x is approaching 0 from the left is going down forever. So that means that the y values are going down, meaning the limit is to negative infinity. If I approach 0 from the right, that's from the right side of my graph because of this plus sign here, we see that the graph is going up forever. So this limit is equal to positive infinity. Now what this means is that we have a vertical asymptote at x is equal to 0, because that's what the x's are approaching, and my answers here are negative infinity and positive infinity. That means that the graph is not going through the x, but it's kind of avoiding it, and it's going up or down forever. Now if you look at this example, we have f of x is equal to negative 1 over x minus 2. You can see that we have a vertical asymptote here at x is equal to 2. If I were to fill in these limit statements, the limit as x is approaching, what number would that be? That would be 2, because that's where I have my vertical asymptote. From the left, on the left side it's going up, so we would write positive infinity. Now the limit as x is approaching 2 from the right, we can see that the graph is going down forever, so we would write negative infinity. So this is a proof of a vertical asymptote, is these limit statements, is that as x is approaching either from the left or from the right, you get an answer of infinity or negative infinity, because it does not go through it. So, and you'll notice here that the denominators, if you set it not equal to 0, that's where you have the vertical asymptote. See here, if I set x minus 2 does not equal to 0, and I add 2 to both sides, I get that x cannot equal to 2. And that's because we have a vertical asymptote there that the function will never touch. So that's kind of a clue as to how to find vertical asymptotes. Now, let's distinguish between what is a vertical asymptote and what is a hole. We saw in the previous examples that we have vertical asymptotes when the denominator is equal to 0. However, that's not always the case when we're given a function and we need to be able to distinguish between an asymptote and a hole. Now, an asymptote, like I showed you before, is that vertical line. So we can see here that we have a vertical asymptote at x is equal to negative 3. Then we have this little open circle. This is a hole. And the hole is at x is equal to 2. So whenever we're writing out asymptotes and holes, we write it down as x equals this and x equals that, because that's the x value that we're looking at. Now, in order to figure out algebraically when there's a hole or when there's a vertical asymptote, what we need to do is take the function and factor it completely, both the numerator and the denominator. So let's look at this graph a second, or rather the function. We have f of x is equal to x squared minus x minus 2 in the numerator. This can be factored to x minus 2, x plus 1. Now in the denominator, we have x squared plus x minus 6. If you factor that, we would get x plus 3, x minus 2. Now you'll notice that if I were to simplify this, I can cancel out these x minus 2's. And I would be left with the function x plus 1 over x plus 3. The factor that canceled, that's where you have the hole. See, if I were to take the factor that canceled, x minus 2, and make it equal, or rather not equal to 0, we would get that x does not equal to 2, which is exactly where I have the whole. And then whatever I have left over, if I set that denominator equal to 0 or not equal to 0, we get that x cannot equal to negative 3, which is exactly where I have the vertical asymptote. So to kind of break this down, the factors that cancel, that factor you set it equal to 0 and you solve for the x, and that gives you the whole. The factor in the denominator that does not cancel, that's where you would have the vertical asymptote. And all of this is outlined here as well, in case you prefer to read it later in your notes. Now let's practice this. We're going to first find the vertical asymptote, the whole, and then finally the domain of each of these functions. When you're trying to find the vertical asymptotes and the wholes, you need to factor regardless. So we're going to take this, both the numerator and the denominator, and factor. The numerator here cannot be factored, so that's just x plus 3. The denominator, x squared minus 9, is a difference of squares, which can be factored to x plus 3, x minus 3. My x plus 3's cancel, and I'm left with the function 1 over x minus 3. So here we go. What's left over in the denominator, that's the vertical asymptote. So x minus 3 cannot equal to 0. So we have a vertical asymptote, if I add 3 to both sides, at x equals 3. That's where I have that vertical. Now the whole is the factor that canceled. So I set x plus 3 equal to 0 and solve for x. If I subtract 3 to both sides, I get that x is equal to negative 3. So that's where I have the whole. Now for the domain is affected by both the vertical and the whole. And that's because these x values here would be excluded, whether it's a vertical asymptote that the function never touches, or the whole where you have some undefined value. So you can always put this on a number line if you'd like to kind of give you a clearer picture. We have the two numbers, negative 3 and 3, both of which would be excluded from the domain. So the domain of the function would be from negative infinity to negative 3, u negative 3 to 3, u 3 to infinity. Now I kind of use does not equal and equal interchangeably, but basically I write the does not equal just to signify that those are values that are not included in the domain. But since I was finding the wholes and the equations of the vertical asymptotes, you can also use equals. I mean, it's really up to you as long as you understand what everything means. Now here for this next one, we have g of x is equal to x squared minus 5x plus 4 over x squared plus 3x plus 2. So first we're going to factor everything. The numerator can be factored to be x minus 4, x minus 1. And the denominator can be factored to be x plus 1, x plus 2. In this case, nothing cancels. In order for a factor to cancel, they have to be identical. So since nothing cancels, that means that both of these factors here in the denominator would be my vertical asymptotes. So we have that x plus 1 is equal to 0 and x plus 2 is equal to 0. And if I solve for each one, I get that x is equal to negative 1 and x is equal to negative 2. So those are the equations of my vertical asymptotes. X equals negative 1 and negative 2. Since nothing canceled, that means that there are no wholes. And that's okay. You don't have to have everything on your graph. Now the domain, remember that these are vertical asymptotes. Therefore, they would not be included in your domain. So you can put these numbers on your number line if you like, obviously putting them in numerical order. These numbers are excluded, but everything else is okay. So my domain would be from negative infinity to negative 2, union negative 2 to negative 1, union -1 to infinity. Now let's look at this next example. We have x squared plus 8x plus 15 over x plus 5. If we factor the numerator, we get x plus 3, x plus 5. And the denominator cannot be canceled, so that would be just x plus 5. Cannot be factored. Now when I look here, I have these two x plus 5s, which can cancel, leaving me with nothing left in the denominator. So my function h of x is now just x plus 3. That means since there's nothing left in the denominator, there are no vertical asymptotes. But we do have a whole because we have a factor that canceled. So that means that x plus 5 equals to 0 is where I have that whole. If I solve for x, I get that x is equal to -5, and that would be the whole. Now your domain, remember, is affected by both vertical and wholes. So we can put that -5 in our number line. We have to exclude that number, but everything else is okay. So my domain would be from -infinity to -5, union -5 to infinity. Now let's look at one more aspect of rational functions, which is horizontal asymptotes. So rational functions have three possibilities for what's called discontinuity, meaning that the function is not continuous. We have vertical asymptotes and wholes, which we've already looked at, but now you'll also notice that we have horizontal asymptotes, which are the horizontal lines where the function will never touch. Now by looking at this graph, we can see that we have a horizontal asymptote here at y is equal to -1. Keep in mind that all of your asymptotes are lines, so they should always be written as equations of lines, and I'll keep reminding you of that later on. So here we have this horizontal asymptote, which affects the range of your function and also your end behavior, which is what these limits are, which is something that we should be more familiar with since we did this earlier in the year. Now what this says is the limit as x is approaching -infinity, so I'm looking at the left side of my graph, my function, those y values, are leveling out at that horizontal asymptote. Remember, it's never going to cross that horizontal asymptote, so it equals to 1. And then the limit as x is approaching +infinity, so the right side of my graph, is the same thing. My y values here are increasing towards 1, but it's leveling out because it can't cross that line, so it's going to equal to 1. So these limits are proof of horizontal asymptotes. Now the range is affected by those horizontal asymptotes, as I said. Since the graph never touches that line, that means that y is equal to 1 has to be excluded from the range. So if you look at your graph, we have all of these negative y values, we have all of these positive y values, but at y is equal to 1, we have a blank space. So the range would be from -infinity to 1, union 1 to infinity, because it's every single number except for when y is equal to 1. Now, how do we figure out we have a horizontal asymptote algebraically? And this is how. You have 3 rules. And all of these rules just depend on one thing. You're going to look at the degree of the numerator and compare it with the degree of the denominator. As a reminder, the degree is the highest exponent of x in either the numerator or the denominator. So these are your 3 cases. If the degree of the numerator is smaller than the degree of the denominator, meaning that the highest exponent of x in the numerator, in this case is 1, is smaller than the highest exponent of x in the denominator, which is 2, then you have a horizontal asymptote always at y is equal to 0. If the degrees are the same, so you'll notice here that in this numerator we have a degree of 1, and here in the denominator also a degree of 1, then what you do is you divide the coefficients of that leading term. So we have 4 divided by 2, so we have a horizontal asymptote at y is equal to 2. Then finally, if the degree of the numerator is larger than the degree of the denominator, So here we have a degree of 2 in the numerator and a degree of 1 in the denominator. Then that means that there is no horizontal asymptote. So let's put all of this now into practice. We're going to find vertical asymptotes, holes, horizontal asymptotes, the domain, and the range. First, here we have the function x squared minus 2x minus 3 over x minus 2. To find all of this information except for horizontal asymptotes, we're going to need to factor. So we might as well do that. In order to factor this numerator, x squared minus 2x minus 3, that is x minus 3, x plus 1 over x minus 2. Now nothing cancels. So since nothing cancels, that means I already know that we have no holes. Now for the vertical asymptotes, that's when the denominator is equal to 0. So if we solve for x, we get that x is equal to 2. So that is the equation of my vertical asymptote. For the horizontal asymptote, you're just going to look at the original function and compare the degree of the numerator with the degree of the denominator. The degree of the numerator is 2, and the degree of the denominator is 1. So since the numerator has a degree that is larger than the denominator, then that means that there is no horizontal asymptote. Now the domain is affected by both the vertical asymptote and the hole. Since we only have a vertical asymptote, that means that my domain is all the numbers except for x is equal to 2. So the domain would be from negative infinity to 2, union 2 to infinity. Now the range is affected by the horizontal asymptote. Since there is no horizontal asymptote, then that means that there is nothing restricting the range, so therefore the range would just be negative infinity to infinity. Now let's look at this next example. We have 2x squared minus 4x minus 16 over x squared minus 4x minus 12. In the numerator, I can factor out a 2 first, which would give me x squared minus 2x minus 8. If I had continued factoring that, I would get 2, and then the factors that would give me x squared minus 2x minus 8 would be x minus 4, x plus 2. When I factor the denominator, the two numbers that multiply to give me negative 12 and add to give me negative 4 are negative 6 and 2. So my factors would be x minus 6, x plus 2. The x plus 2's here cancel. So that means that I'm left with a simplified rational function of 2, x minus 4 over x minus 6. Now whatever we have left in the denominator, that's my vertical asymptote. So x minus 6 equals to 0 would be where I can find that vertical asymptote. So we can add the 6, giving me a vertical asymptote at x is equal to 6. Now the whole depends on the factor that canceled. So I take that factor, the x plus 2, and I make it equal to 0 to solve for x to get the location of the whole. I would have to subtract the 2, so x is equal to negative 2 is the location of my whole. For the horizontal asymptote, we look at the original function and compare the degree of the numerator with the degree of the denominator. Since the degree of the numerator is 2, and the degree of the denominator is also 2, then we just divide these coefficients, since they are the same. Now this is 2 divided by a 1 that we don't see, and 2 divided by 1 is 2. And the equation of the horizontal asymptote is y is equal to 2. Remember that all of these asymptotes are lines, and we have to write them as equations. So that's why the vertical asymptote is x is equal to 6, and that's why the horizontal asymptote is y is equal to 2. Now the domain is affected by your vertical asymptote and the holes. And I mean, look at how it's written, right? We have x equals and x equals. So these are affecting domain, since domain is the x's. and the range is affected by the horizontal asymptote since that's a y, since range represents y's. So my domain, we have to exclude -2 and 6, but all of the other numbers are okay. So my domain would be from -infinity to -2, union -2 to 6, union 6 to infinity. And again, if you prefer, you can always put this on a number line so you can see exactly how it comes into play. These numbers are excluded, but everything else is fine, and that gives me the domain of my function. Now the range is affected by the horizontal asymptote, so I have to exclude 2 from the range, meaning that my range would be from -infinity to 2, union 2 to infinity. Now let's look at this final example. We have 2x minus 1 over 2x squared minus 7x plus 6. I can't factor the numerator, but I can factor the denominator. But in this case, I would have to use the AC method, since we have a number in front of the x squared that I cannot divide from every term. So first, we're going to figure out what is A times C. 2 times 3 is 6. And the two numbers that multiply to give me 6, but add to give me -7, are -6 and -1. So now I'm going to rewrite that quadratic, so 2x squared, and I'm going to replace b with those two numbers. So minus 6x minus x plus 3. Now I factor by grouping. 2x squared minus 6x have a 2x in common, leaving me with x minus 3. And then we have -x plus 3. Remember that we want that second factor in the parentheses to be identical, which it almost is, except they're opposite sides. So I'm going to factor out a -1, which leaves me with x minus 3. So now I'm ready to rewrite my function. We have our numerator, which is 2x minus 1, over the denominator, the factor that is identical in the parentheses is 1, and then what's left over is my other factor, which is 2x minus 1. Here, my 2x minus 1's cancel, and I'm left with a simplified rational function of 1 over x minus 3. So now, my vertical asymptote is when the denominator is equal to 0 of my simplified rational function. So if I set x minus 3 is equal to 0, we get a vertical asymptote at x is equal to 3. The whole is located at the factor that was canceled, so we have to set 2x minus 1 equal to 0 to solve for x. I would have to add the 1, leaving me with 2x is equal to 1, and then divide the 2, which leaves me with x is equal to 1/2. So that is the location of my whole. Now the horizontal asymptote depends on the degree of the numerator and the degree of the denominator. The degree of the numerator is 1, which is smaller than the degree of the denominator, which is 2. That means that I have a horizontal asymptote at y is equal to 0. Now the domain. Remembering that the domain is restricted by the vertical asymptote and the whole. So my domain would have to exclude 3 and 1/2. And again, you can put this on your number line. 1/2 comes before 3. These numbers are excluded, but everything else is fine. So my domain would be from -infinity to 1/2, union 1/2 to 3, union 3 to infinity. Now the range is affected by my horizontal asymptote, and therefore it would be -infinity to 0, union 0 to infinity. And those are all of the properties of rational functions.